you can still hear me. I don't have a supplemental mic because last week when I was trying to show the video, it gave me an error. So I thought we'd just go without the mic for now. So I do want to look at some kind of go over what we're looking at today, or not just today, but also this week, and want to kind of again kind of touch base. So if we sort of look at our schedule, so this is week 7, and so lab this week is going to be work on your casting project. And so for Tuesday from 8 to 10, I will be in S130 and Teams. So you don't have to come, you don't even have, you don't have to call in. But my thought was that this is time for you to work on your project. And if you want to go to 1:30 and work there, or if you want to just kind of call into Teams if you happen to have any issues. Now, I hope, I'm never quite certain when Canvas is being helpful. I believe I sent a message to those of you who are in the Wednesday lab, and that I am not, I don't believe I'm going to be available to be either on Teams or in person on Wednesday. So I'm just going to say see Canvas message. So you are more than welcome to come to Tuesday. I think that between the size of the Harley lab and if we need to have some overflow, we can do that. You can come on Tuesday. Also, I did suggest some other times where I might be available. So I did want to, again, just make sure that we're kind of aware. Nothing is required this week. This is time for you individually or as your group to work on it. I hope there are no additional issues with SolidCast. I know 2 people did have to reinstall SolidCast, so hopefully everything is going fine. I also did cancel my office hours on Wednesday, so, but again, I can be available if needed. So that's the first thing. We also have our plastics reading assignment is due this Thursday, and then we have machining homework is due Friday. Week 8, lab is going to be surface roughness and an opportunity to look at some parts, some plastic parts, some powder metallurgy parts, and some machine parts. And then we will have an exam on Friday of next week. I will talk a little more about that, but my plan is for the second exam for students to be able to bring in a sheet. There will be machining calculations on there. So instead of supplying formulas, I will allow students to bring in a sheet, 8.5 by 11, one side, and we'll talk more about that. But I wanted to at least get this kind of going and especially talk about this week's schedule. Okay, so, and again, since I figured out how I can see the chat, that doesn't mean I always pay attention to it. But if you have any questions or you want to say something, either speak or you can attempt to put it in the chat and we'll see if I can catch it. So we're going to go back to our alternative machining or material removal processes. I did put the entire video that we're watching clips on into Canvas with the times that are useful, there are some other processes that you might find interesting as well. On Friday, we were talking about water jet. And again, in water jet, we are looking at our the machining and the material removal is coming from a high pressure, high velocity stream of water. We talked about some of the advantages or some of the characteristics and a little bit on the units themselves. And I think this is where we were when we finished on Friday. And again, you can see that we have a lot of intricate parts possible. Here is a puzzle, and so this is paper, and so the velocity is high enough, the stream is tight enough that you actually can do paper and cardboard in water jet without issue on there. So you can kind of see how thin we have it. I do want to introduce sort of a new word, and that is kerf. And so when we talk about kerf, this basically is the sort of in a material removal, the thickness of material removed. And sometimes we also refer to that as the material itself that's removed. So if there's a statement that says water jet has low kerf, what we're talking about is sort of this material that ends up getting removed. So we might also say that, you know, rough milling has a large kerf. So kerf is something that we do tend to see in these material removal. This is sort of the part was what was inside. This was sort of the starting blank, so to speak, from water jet. So you can kind of get an idea of how thick you can go as well. Okay, so let's kind of consider some characteristics of parts. Now, we have oxyacetylene, and we kind of know oxyacetylene is big tolerances are needed, very rough surface. And when we look at the feed rate or how fast you can go for really thick parts, it's very good. But for the three more finishing processes, we really want to kind of have an idea of feed, tolerance, and surface. And so when we watch the videos, we can kind of get an idea of, oh, they may mention with a feed rate of this or a tolerance of this, but that's something that we do want to be aware of for these particular processes. Sometimes we will have numbers and sometimes we will not. But in terms of the overall characteristics of water jet machined parts, one of the big one is no heating. So there is no heat affected zone. So we don't have to worry about any changes in material property due to heating. Now, if we want to look at surface roughness, so if we look at, again, the surface roughness, we're kind of in the 8 to 32 microminutes, not micro, I don't know where I got micro inches. And now I'm just going to kind of note here, EDM and laser can do slightly better, so can do better. So water jet gives us, you know, the surface is good compared to some others, but EDM and laser actually do a little bit of a better job than that. And again, if we kind of look at feed rate, so this is going to be moderate on the feed rate. And so it is going to be faster than EDM and slower than laser. And sometimes in the video, we can kind of pick up different feed rates. Any feed rate will depend on thickness and material. So our metals are going to be a slower feed rate, but water jet's kind of on the moderate end. And then it is going to be good for food products, paper products, and composites. And so we're really kind of saying that we are versatile in the workpiece materials. So we're not really looking at, so one of the things is almost any material is going to be able to be cut by water jet. If it's a harder material, we may have to add abrasives, but we're not looking at, for the other two, there are going to be some material limitations. And then in terms of the actual machine costs, the machine costs are fairly good going on here. We don't have dedicated tooling, so it is, I'm going to say it's computer controlled for the shape. And what this means is a single part is possible. And again, that makes it nice for custom parts. Okay, that actually is what I wanted to talk about in terms of water jet. I am again going in an opposite direction of what how I had set this up. On my notes, we're actually going backwards. So we're going to next talk about laser. And we also, I want us to kind of look a little bit at a video, but after we go through a few of the parts of the slides. So if we want to talk about laser beam machining is probably one that has more market share. You're likely to encounter laser cutting or laser beam machining. Really, I am not aware that there's a big difference between the terms laser beam machining, or sometimes this is called LB, or laser cutting. Again, sort of a terminology issue here. Lasers are becoming more and more useful, more and more used. Now, we are going to use a highly focused light energy to remove material by vaporization. And so oftentimes the CO2 laser is the common form. Now, we are looking at thermal energy to remove the material. So we do have a heat affected zone. The size of the heat affected zone is very dependent on the size of the beam, so to speak, that's causing the vaporization and heating. So it is going to be small because we have a very concentrated energy, and generally it's not going to be there as long. Now, the vacuum not needed, this is related to one of the first high energy processes. Oftentimes we can use the same process for welding as we can for a cutting or machining. So some of the first high energy processes were electron beam. There is no longer a commercial process that I'm aware of in terms of electron beam machining. There is some electron beam welding, but for an electron beam, you needed an incredible vacuum. And so your parts and everything had to be enclosed in a vacuum. A laser allows you to have a very highly focused, high intense beam of energy without a vacuum. So that is huge. If you're also thinking, well, there's probably no radiation. Don't you have radiation from an electron beam? Yes, you do. So this vacuum is not needed is really very powerful. And also what's kind of interesting is that lasers can be focused and transmitted with mirrors. And we really don't need to have physical contact. And a laser can go through a transparent material. So you can actually process through a transparent material. Some of this we will also talk about when we talk about laser welding. Okay, so we're somewhat, there is some limitations on what kinds of materials we can do laser machining on, but we can do metals, plastics, ceramics, glasses, and composites. If your composite has significantly different melting temperatures, that could be an issue. What we also see is with reflectivity. So notice that we need low reflectivity. So a material that is really reflective is going to have some issues. So we also want to kind of note that a reflective material has some issues. So bright, shiny objects do not laser beam machine well, but it is a very versatile process. Okay, again, we're just looking at we have our laser, we have our workpiece. We do have a little bit of distance between the tip of the laser and the workpiece. It is all CNC controlled. So again, we can do we have that coherent stream of light to vaporize or just chemically ablate the material. Okay. So again, here is a laser cutter in action. You can sort of see how close it is to the material. Here again, we can oftentimes do attach the laser to a CNC or either a CNC table, and we can kind of move it easily. I am going to move to, let's look at the little bit of the video clip on this, and I am unsharing so that I can, when I do go back and share, I can include the sound. And we're going to see a little bit of the end of the water jet, but we will again look at laser, look at the materials, listen for anything about tolerance or anything about feed rates as well. So let's give laser a go. And here we go.
Tolerance on the spanner is plus or minus 0.2 of a millimeter, and the edges must be square. Laser generators have a capacity of 1 to 3.5 kilowatts, and this energy is focused on a spot having a diameter of 0.2 of a millimeter. A 2 kilowatt generator will cut 12 millimeters mild steel at 1100 millimeters per minute using oxygen as an assist gas. For cutting stainless steel and aluminium alloys, high pressure nitrogen is used. This is called clean cut. Non-metals use compressed air. Laser cutting allows a new flexibility in design, as shapes that were previously considered impossible can now be cut. This industrial CO2 3.5 kilowatt laser generator produces enough power to cut 2.5 millimeter stainless steel at a feed rate of 2 meters per minute. The laser beam from the generator is reflected via a series of mirrors to the cutting head. These mirrors must compensate for the cutting head movement, a very complicated task when 3D laser cutting is performed. The Laser Lab profile machine has two tables, 3 meters by 1.5 meters, that pass under and over each other, allowing one table to be unloaded and then reloaded, while material is being cut on the other table, giving an improvement in machine productivity of up to 50%. With 2,500 kilopascals of high-pressure nitrogen, clean cut, tolerances of plus or minus 0.1 of a millimeter can easily be maintained over the shape. The cut width is less than 0.2 of a millimeter. The complete shape is cut out in 1 minute 38 seconds. The edges are clean, square and smooth. This process is ideal for medium-sized production runs where the cost of a die set would be prohibitive. It is also perfectly suited for just-in-time requirements, where small batch sizes are required, as changes from one material to another can be accomplished within 1 to 2 minutes. The program for cutting this acrylic sheet has been downloaded from a CAD station, or could have been imported from a customer's data file into the sophisticated CNC controller of the Laser Lab profile machine. The feed rate for cutting this 3mm acrylic sheet is 20 meters per minute. When cutting acrylic sheet, compressed air is used with the laser to remove vaporized material from the cut. All 14 shapes are cut out in under 3 minutes. Using compressed air, wood, fabrics, plastics and foams, provided they do not give off noxious fumes during the process, can be easily cut, non-ferrous alloys being more difficult. In this case, a pre-painted plywood is cut into a number of shapes that have been carefully designed and nested to give a maximum number of units per sheet. Whether it is a small production run of 10mm steel plates, one component of complex shape required for prototyping, or runs of a few thousand, then laser cutting should be considered.
Okay, so that is fun with laser cutting. And one of the things that you may have noticed compared to the water jet is how fast that laser cutting is going. So laser, and if you, I know it's kind of hard to remember, oh, what were those speed rates on the other ones? But just the head moves much faster. You may have noticed that it does go faster with the acrylic than it did with with the steel. But laser is going to have a much faster feed rate compared to water jet. There's sometimes I often ask myself, like, why are you making those particular parts? But you did get an idea of the various materials. And one of the things when we think about a laser, we think about very small holes. So laser, again, like some of those small holes and features work very well for a laser machining. These are both examples of some laser cut parts. Here's, we have a very intricate detail going on here. And here we have very straight sides, holes. And because it is computer controlled, we again have that situation where we can do a very small number or a larger number. So if we want to kind of go back and, kind of look at our characteristics, and I realized that I was missing one on water jet. So we'll go back and pick that one up. So one of the first things is it is a faster, meaning higher feed rate than both EDM and water jet. Very small holes are possible. And it actually, and that one part where it talked about a prototype part that had a number of holes and some slits, very good, very effective part for laser cutting. Okay, we have good tolerances, and now tolerances is what I forgot to put with water jet, plus or minus 0.001 inch. So it is better than water jet. Water jet tends to be plus or minus 0.003 inches. Not as good as EDM. And EDM, actually, we can get down to 0.0002 inches. So it's good tolerances are available, but not quite as good as what we can get with EDM. Nice thing is the edge is straight, and especially compared to shearing. Because remember, in shearing, we do not get a straight edge, but in laser, we do. It is going to have a small heat affected zone. It is slower with thicker materials and steel. And then highly reflective materials can be an issue because if the material reflects too much, then you're not going to be able to. You need the material to sort of be able to absorb the energy in order for it to cut. But laser is an awesome process, and it is likely to be one that you're going to see quite a bit. There also are, also I am going to do the CNC, so we can do a small batch as well. So laser, again, very, very good process. Okay. The last one I want to look at is EDM, and let's kind of give that one a go a little bit. So EDM is electrode electric discharge machining. And so in EDM, we are looking at, again, this is going to be a vaporizing kind of process. This is more of a thermal process, but it works in a different way than with lasers. We're removing the material by a series of discrete electrical discharges or sparks. So we will have an electrode. So we have an electrical circuit, and we have like the anode and the cathode. So we get very high, localized high temperatures. You melt or vaporize the material in the immediate vicinity of the discharge. It is not a process, it is a process that actually works very well for hard materials. Now, we do have to have a conductor, so it is a material, or excuse me, a process that is limited to electrical conductors. So pretty much metals going on here. There is a wire process for cutting, and that sometimes is referred to as wire EDM. And that has this particular, the wire process, we can do a small quantity or one. The shape process, because we have an electrode, we oftentimes like to have a little bit of a higher process. Okay, so let's sort of look at this, and we'll do the same thing. We'll talk about it a little bit, and then we'll go and look at the video to help us out a little more. So an EDM machine, you know, they're somewhat dedicated. They're not as you know, complex as we might see in other fields, but we do need to have a dielectric fluid. We do need to have the ability to connect a circuit, and you can see that the tool is the electrode, and the tool is going to be the opposite of what we're trying to create, and we just drive the tool into the workpiece. If we look at what's happening in this gap, we actually are, again, getting this spark, and that is going to essentially just melt and vaporize the material. So we're basically just sort of moving our electrode into the workpiece and vaporizing it. So here's the electrode, and that's exactly the opposite shape of what we would produce. Here are some parts that have been EDM'd. We also could see, here's another example of an electrode, and then the part or the shape that it would be producing. Okay. I think that now is probably a good time to like watch the EDM video, which is right after the laser. So here we go with electrode discharge machining.
With electrical discharge machining, the electrode is made out of copper or graphite and is the male shape of the hole to be cut. About 1% of the electrode is lost during the cutting process. The electrode sparks its way into the workpiece in the Z-axis. The workpiece is in a dielectric fluid that controls the spark conditions and also flushes debris from the cut area. Central flushing of the electrode is a common practice.
I usually skip this, but we'll do it.
A broken tap. It is very difficult to remove a broken tap from aluminium, as there is a large difference in hardness between the two materials. To solve this problem, a process was developed in the 1950s called spark erosion. The power supplied to this electrode is 50 volts at 12 amps. Preliminary settings of the machine's spark control are made. Modern machines can automatically vary the power supplied as the area of the electrode changes during its cut. The electrode is lowered and then carefully aligned. The tank is filled with a dielectric light oil, some of which is being pumped out of the center of the electrode. This will later act as a flushing agent. Final adjustment is made to the controls to optimize cutting conditions. The broken tap is being machined away without damaging the surrounding material. After the tank has been drained, the remnant of the tap is removed. The cavity in the die was cut using the graphite electrodes below. A new electrode is required for every new shape that is to be cut. With the advent of CAD workstations and CNC machining centres, very intricate and complex shapes can now be machined. The quality and cost of these graphite blocks varies greatly. The grade selected is dependent on whether a roughing cut or finishing cut is to be made and the rate of electrode loss that can be tolerated during the electro-machining process. The electrode shapes are produced using CNC machining centres having 3D capabilities. A new method of flushing out the debris from the machining process is to move the electrode away from the work and then down again. Resume machining for a few seconds and then move the electrode away again. This causes a very efficient flushing of the surfaces, leading to an increase in the cutting rate and a decrease in the rate of electrode loss and hence better shape definition. The electrode can be rotated like a milling cutter, and the CNC controller moves the electrode around the shape to be machined. This gives rise to improved surface finish. Wire cut is a form of electrical discharge machining that is ideal for the cutting of precise shapes from previously hardened and tempered blocks of steel, at the same time producing a fine surface finish, thus making the completed die shape that requires no further heat treatment with its inherent possibility of distortion. The process is ideal for the production of extrusion dies and die sets. The brass wire threads through the work at 180 millimeters per second, and the feed rate for a 10 millimeter thick steel plate would be 8 millimeters per minute. The work moves in the XY direction relative to the wire. With CNC controllers, it is possible to angle the wire so as to offset the top shape from the bottom shape, or rotate the top shape relative to the bottom shape, or scale the top shape to the bottom shape. This is particularly advantageous when making a punch and die, as the larger top face of the punch can be made to fit the smaller hole on the bottom, thus making the punch and die from the same piece of metal. The shapes that can be produced are limitless. The brass wire that is used has a diameter of 0.25 of a millimeter and is only used once, it then being sold for scrap. The wire cut machine is threaded up like a sewing machine. To get the wire through a previously drilled hole in the work, a small jet of high pressure water is used to guide the wire through the work and thread the rest of the machine. A large column of deionized water is used to surround the wire. The head is lowered and cutting proceeds. This stack of 30 galvanized iron sheets is being cut so that the sheets can be used in a pilot run to establish that the shape is correct for the final forming of the product. The same program can later be used for cutting the punch and the die.
Okay, there we go. So I do, again, like the, some of the examples and to allow you to be able to kind of see what's going on. So again, what we're doing in, whether it's the wire EDM or it's the standard like shape or sinking EDM, is we are generating a spark between the electrode, which is either going to be the shape we're interested in, and we're just plunging that into the workpiece, or it's from the wire, and there's always going to be that dielectric fluid around it. So we are generating that spark. And again, if we look at the wire process, the wire is acting as our electrode, and we're just sort of, moving that wire through the material. Wire EDM is more versatile in terms of the shapes, also in terms of it's a computer program that's going to do it. So wire EDM, I have actually a little more experience with wire EDM than I do straight EDM. Now, if we want to kind of consider some of the characteristics, now the EDM, this is where we can get really good tolerances. Notice that our laser was 0.001. So we are 5 times better, we could say that, in terms of tolerance. So EDM is, not only is it really useful when we want to have a very hard material, we can get very good tolerances. So it is also good for delicate parts and thin walls. Not to say that the other two processes aren't. Hardness of the workpiece is not an issue. So we don't really have to, this is a process that for our really high hardness materials, our hardened steels, works very well. We are limited to only conductive materials. So we cannot do EDM on plastics, on ceramics, and many composites unless it's like a conductive composite. We can do very complex geometries. And so we kind of noted here that you could sort of create a prototype sheet metal, okay, which I think is kind of interesting. So you can create your and then the punch and die. If you're using it for shearing and you need more of a clearance versus if you're doing it just for your general forming. And so you can actually, again, because you're creating a match set, that is actually very useful. And the hardened steel is not going to be an issue for EDM. They don't kind of mention this, but it is a very slow process. I believe the feed rate that was mentioned was 8 millimeters per minute. In laser, there were some of the examples where it was meters per minute. So EDM is a slow process. If you were sort of thinking, oh, we've got to do that spark, and that is sort of its negative, is how slow it is. There also is an issue with a recast layer and heat affected zone. So this recast layer, we, often we see that the metal, some metal that melts will sort of refreeze on the surface. This is not great. There is some degradation or some loss of mechanical properties. Oftentimes that recast layer is just removed on there. Okay, so this oh, okay. I'm like, why do I have it twice? That's right. I think I was going to like write this down and then I didn't get rid of the other one. Okay, so I think that if we look at these, all of these processes, that we can sort of see again this idea of tolerance, of feed rate, of surface finish, and kind of make a decision or go with what is the best process for a particular application. In all cases, I shouldn't say in all cases, but what we really are interested in for these, the processes that we've looked at, and we cannot look at anything, you know, in great detail. We just kind of want to be aware of the variables in terms of again, tolerance, surface, feed rate, and any of the restrictions that are there. I used to be able to borrow a EDM process. The example of an EDM that I had was for the channels in what would be called what was part of the machine in a bypass situation, that the blood would flow through to be regulated in a temperature environment. And so the tolerances were very tight, and cost was not as much of an issue in terms of machining time. But most common of the process that we've talked about is probably the laser beam machining. Okay, on Thursday, we will, I will likely go over